How is orbital insertion optimized to save rocket fuel? Imagine launching a satellite into space and wanting to do it with as little fuel as possible. That's where orbital insertion techniques come into play, making space missions more efficient and cost-effective. When a rocket pushes a satellite into orbit, it needs to perform specific engine burns to slow down or speed up the spacecraft at just the right moments. The goal is to reach the desired orbit while using the least amount of propellant. One common way to do this is by using a transfer orbit called the Hohmann transfer orbit. It involves two engine burns, the first to move the spacecraft from its initial trajectory into an elliptical transfer path, and the second to circle the satellite into its final orbit. This method takes advantage of gravity and the spacecraft's velocity at certain points, making the process more fuel efficient. Timing these burns is also key. Engineers usually perform the main insertion burn at the point where the spacecraft is closest to the planet, called the periapsis. This is because the spacecraft is moving fastest there, and a burn at this point produces more energy change for less fuel. This effect is known as the Oberth effect, and it helps maximize the impact of each engine burn. Adjusting the ascent profile, or the way the rocket climbs through the atmosphere, also helps save fuel. Engineers simulate different paths and engine settings to find the best combination that meets the mission's needs without wasting propellant. Sometimes, they combine different propulsion types. For example, chemical rockets give a quick burst of high thrust for launch and initial insertion, while electric propulsion systems can gradually raise the orbit over time with less fuel. Mission planners use advanced computer models to simulate how the vehicle moves through space, accounting for atmospheric drag, gravitational influences, and engine performance. These models help identify the most efficient trajectory that uses the least fuel. In short, orbital insertion is optimized by choosing the right transfer orbit, timing engine burns at the highest velocity points, fine-tuning ascent paths through simulations, and sometimes combining propulsion methods. These strategies help save fuel, increase payload capacity, and make space missions more successful and affordable.